acid-base titration, example 3. Take a moment to read through this question, which provides you the liters of solution of a 0.1 molar weak acid. It gives us an acid dissociation constant, Ka, and tells us that it is titrated with 0.2 molar sodium hydroxide. And then it gives us 8.80 as the pH at equivalence point. Part A asks us to calculate the volume of base needed to reach the equivalence point. All right, so what do we know here? Since we're given the concentration of the weak acid and the volume of that solution, we can quickly determine how many acid molecules were added. The number of moles here is simply the volume times the concentration, or 0.08 liters of 0.1 molar solution, therefore containing just 0.008 moles of acid molecules, and each one of those acid molecules contributing one hydrogen ion. Now, like I said, is it monoproctic? Yes. And because it's monoproctic, reacting with a strong base, each sodium hydroxide reacts with one hydrogen ion released from the acid. It's a 1-to-1 ratio. So the moles of sodium hydroxide and thus hydroxide needed to reach the equivalence point is 0.008 moles. Okay, we are almost done with part A. Knowing the concentration of the sodium hydroxide is 0.2 moles per liter, we simply find the volume using a formula. Volume equals moles divided by the concentration in molarity. So that's 0.008 moles divided by 0.2 moles per liter. Notice what cancels out. We don't need a whole liter here. Simply 0.04 liters are 40 milliliters, which is good. And good that we remembered to keep 3 significant figures here when we did that conversion. We are done with part A. Part B, calculate the pKa for the weak acid. So what do we need here? Just the K sub A acid dissociation constant, which is indeed given. We can simply take the negative log of the given acid dissociation constant, Ka, and that'll provide us our pKa. Rock and roll. The negative log of 3.20 times 10 to the negative 5 gives us that pKa value of 4.49. Does it make sense to be 4.49? Yes, it is smaller than 7, which indicates that it is a relatively weak acid indeed. Part C, which is the longest part. What is happening before the titration even begins? We're going to consider the shifting of the original solution when it is first mixed, or as I like to say, inaugurally mixed. The weak acid hydrolyzes water in solution until an equilibrium is established. That's what happens right away, right? It happens immediately, and it occurs before the titration is even considered. Let's set up the Rice table. What do I start with? Well, the original concentration of weak acid was given as 0.1 moles per liter. Hydronium concentration before mixing was essentially 0. Hydronium concentration being synonymous with what we could think of as free hydrogen ion concentration. So what's the change? The weak acid reduces by amount X. Hydronium and conjugate base concentrations will both shift upward by that X amount. Now, K sub A given 3.20 is also related to this formula. The formula for finding acid dissociation constants relates to the concentrations as the products over the reactants. Again, products over the reactants. Is water included? No. Liquid water is not included because it's the solvent, and its concentration stays basically unchanged. Substituting X into that formula as the concentration gives us again X squared on top. Now, can I ignore the denominator? Yes, the shift from 0.1 moles per liter is so small it can indeed be ignored. If the shift were bigger, I'd need to use the quadratic formula, but not here in this case. Solving for x squared equals molarity times the acid dissociation constant. Okay, and then we square both sides, and that tells us that the x value of shifting is just 0.00179 moles per liter. That can indeed be reported as 1.79 times 10 to the negative 3 moles per liter. Again, what does that x represent? Well, in this case, now it represents where the hydronium concentration is, and we'll use that to find the pH. If the hydronium concentration shifts from 0 up to 1.73, then the pH becomes the negative log of that value. The pH of the original acid solution prior to titration is 2.75. All right, that gives us indeed our very first point that we'll put on the titration curve. When the sodium hydroxide is at 0 milliliters, the pH will be 2.75. Oh, let's consider the shortcut. pH is 1/2 the difference between the log of the weak acid concentration and the negative log of its acid dissociation constant. Plugging that into the calculator, we end up having a similar answer. It's always nice to confirm, and it is good for you to keep that shortcut handy. Part D is our titration curve. Where do we start? Originally, before any sodium hydroxide was added, we said the pH was 2.75. So let's mark that and mark it with a slight upward trend starting there. Where is half equivalence going to occur? At 20 milliliters of sodium hydroxide. Why? Well, because equivalence, full equivalence, was at 40 milliliters. So half equivalence will indeed be 20 milliliters. At the half equivalence point, the pH equals the pKa, which was found in part B to be 4.49. The pH at full equivalence is given in the original question as 8.80. To build the curve, which again is definitely not a straight line, add the horizontal leveling area around half equivalence point. That's our buffering zone. At the equivalence point, the graph should rise almost vertically. After that, where sodium hydroxide becomes in excess, the pH levels out near 12.5, typical for a titration ending with a strong base like sodium hydroxide. There is our curve. Now, quick question. How does this titration curve compare to the one that we built in example 2? Example 2 question had a smaller acid dissociation constant, K sub A, than that in example 3. Notice, however, that in example 3, which uses that stronger weak acid, the equivalence point is reached with less titrant hydroxide. So a common misconception in titrations is that stronger weak acids, those with larger acid dissociation constants, K sub A, will always require more strong base to reach an equivalence point. But in reality, the amount of base needed depends on the concentration and on the volume of that acid solution, not necessarily its strength. The strength of weak acid, as measured by K sub A, affects the shape of the titration curve, but not the total moles of base needed to neutralize it. Titration curves shift based on both the acid and base strengths and at solution concentrations. Strong acids and bases dissociate completely, so their curves show a sharp pH rise near the equivalence point at 7. Weak acids or bases only partially dissociate or partially hydrolyze, producing more gradual curves with clear buffering regions. The pH at equivalence points also varies. It's around 7, like I said, for strong acid, strong base titrations, above 7 for weak acid, strong base titrations, and below 7 for strong acid, weak base titrations. Concentrated solutions make pH changes more dramatic, while dilute ones stretch out the curves and flatten the slope. Did we calculate what we needed to? Did we sketch a titration curve? Did we hit all of the parts in example 3? Yes, we did. Heck yes. Let's go.